Awesome. Are we recording? We are good to go. All right, awesome. Thanks everyone for making it to the Zero to Hero machine learning session. It's the Lovable Guide Part 2 on all things data science, data engineering. I've been having such a great time with you all, sharing what I know about data science, from building teams to actually just learning more about machine learning. So some of you asked a couple of questions in the last session about, how do you even measure the success of machine learning projects? What is machine learning, et cetera, et cetera. Some people even wonder, like, what's the difference between supervised versus unsupervised learning, and like, what the hell does it mean when we start getting into deep learning and reinforcement learning? So that's what this session is all about. I want to cover what you need to know about ML in a very condensed session, right? So I'm almost like your professor for this semester, but the semester is only 1 hour long. And we'll keep this session interactive, so feel free to ask any questions that you may have at the end or even in the chat. I'll try to get to them. Let me pull up the chat just in case I miss any messages that you may have. Anyway, I want to cover a couple of different points here for this session, and it's really to cover just the basis of what is machine learning really, beyond all the buzzwords, beyond marketing calling things artificial intelligence or ML based. What does that actually mean? What does that look like in the industry? How does it work? And I'll even show you all a little snippet of what training involves and like what does it actually take to deploy ML models and solutions such and such. Again, this is just like an intro level course. So if you come out of this with just nothing else but 1 or 2 snippets of knowledge, totally fine. I hope you find this relaxing, enjoyable, and fun. So we're going to be covering all of these aspects, if I'll be able to advance my slides. All right, so I just want to get started with the 101s. What is AI? What is ML? How do you even begin to think about it, right? We know that there's a lot of really great use cases for machine learning and artificial intelligence. And we see that in the transportation industry with automated cars, smarter cars, right? We see that in the healthcare industry, lots of really great advancements and just really great ways of being able to produce accurate diagnosis through ML models that can, detect some of the things that we even ourselves manually cannot detect or begin to understand. There's also really great advancements in the computer vision and photography space around being able to kind of detect different objects given a particular image, and also being able to do this real time, right? And these are really helpful for use cases that involve just smarter and smarter applications that can, assist us in learning or assist us in beginning to classify certain objects in the world. And again, like there's a little last bit here around natural language processing, building smart, auto translate robots, smart whatever type assistants, right, that can understand language and work on it in a very interactive basis. And so, you may think like, oh yeah, a lot of times, a lot of organizations say that something's powered by machine learning and artificial intelligence when it's not. It's really just a bunch of if statements and some programming, and it doesn't actually involve any learning or anything that's really novel in terms of processing data and understanding it. But there are real use cases here, and these are the real use cases that we're talking about for this. And so I want to make a distinction because, sometimes artificial intelligence can feel like a separate thing from machine learning, and then there's all this speak around deep learning. So I really wanted to kind of break it down for you all because sometimes we can get looped into the terminology and kind of lose our way. So really, I want to start by covering artificial intelligence, and really this is the umbrella term for a lot of the practical approaches that we're using today to build to build human behavior into our applications. So a lot of the practical steps that make artificial intelligence systems really viable is what we're doing in the machine learning space. And if you were to take it another step further into deep learning as well, you'll be able to find that this is how we're basically building our AI systems, as we call them, AI systems. And really with machine learning, you're thinking about data in two kinds of ways, right? It's either based in linear algebra or based on probability, and really you're building models that can learn based off of data that you feed it. And we'll go into more depth on like how exactly, what are the different types of learning that machine learning models do, and how can you even build models that sustainably solve realistic problems? Because okay, it's a machine learning model. What is it actually doing though? And this problem is actually harder to solve when you're asking a deep learning model, like, what are you actually doing? And so there's a whole kind of separate area within machine learning that focuses on building neural networks, multi-layered neural networks, to learn and solve some of the more complex challenges that we have today. We're doing it at a really nice pace, right? Wow, did I just skip a couple slides? There you go. So, what if statements didn't exist and we needed to work with machine learning approaches? How does that work? And what is even machine learning, right? And if we want to think about it, it's that learning process where we're using specific algorithms and approaches to make and learn make predictions off of data that we're feeding it. Right. And so if you were to make a machine model learn, there's a couple of different ways that you can go about it. And depending on the different ways of learning, which we'll cover, you'll be able to solve different problems and kind of different use cases. And we'll talk about those use cases as well. So I'm going to take a little pause there. If anyone has any questions about machine learning so far, just let me know. We may also cover that question in later slides. All right, so there's kind of three main ways to learn in a machine learning model, right? To train a machine learning model, you can use supervised learning, unsupervised learning, and something called reinforcement learning. And we're going to cover all of those aspects. So in supervised learning, there's actually two kinds of use cases for supervised learning. And the first way is called classification. And so this is like, given some data, right? Tell me if this person's happy or sad. And so classification can be binary classification. Is this a human face? Yes or no. It can be multi-class classification. So you can have a yes, no, maybe category, right? Is this person happy, sad, or we don't really know, or maybe they're neutral? Can this person, based off of the data, repay a loan that a loan model that we're having this application loan, or will this user click on some ad based off of the data that we give it? So classification problems are more of a yes, no answer. But that's what supervised machine learning typically solves in this space. And if you wanted to solve an additional type of problem, like, on a scale of 1 to 10, how happy or how sad is this person? That's a regression problem. So a regression problem is a numerical output that you get back. So if I were to say, I want to know what percentage likelihood is this stock going to go up in 2 days, then I may have a supervised machine learning model that is a regression, that solves a regression problem and gives me back a percentage, or gives me back a projected cost of a particular stock that I'm interested in. So it's interesting because basically I give it some data, and typically when I give it the data, it's labeled data. So what I mean by labeled data is, if I want to have a classifier, that's what we call it. If we want to solve a classification problem where I'm only feeding it pictures of cats, and I want to be able to know if this is a cat or a dog, if this is a cat, yes or no, then I may have some data in my training set that I'm feeding into my machine learning model that's pictures of turtles, and I say that this is not a cat, right? So you need to have some type of, you typically in supervised machine learning, you have some input and then a label if it is a cat or if it's not a cat. So you need to have some kind of truth, 0 or 1 binary output there. And what happens in that classifier, or these regression learner models, they learn some type of function approximation to be able to estimate whether or not, given some input like a picture of a dog, that this is not a cat, right? So you end up learning a function based off of the training data that you give these models. Another kind of learning that you'll typically hear about when we talk about machine learning models is something called unsupervised learning. So in unsupervised learning, I actually don't have labeled data. I just have data. And this can be patient data, this can be medical data. So say, for example, I'm building some type of machine learning model that will tell me how am I at risk for diabetes or not? And my data can have, I don't know if I have diabetes or not. I just give it data, and then it'll group that data. It'll do 2 things. You can typically, with unsupervised learning, solve clustering problems. So you can basically do some linear algebra, some probabilities around different groups of data that you feed it, and that's what it learns. There's also a really great use case for unsupervised learning that involves dimension reduction. So in dimension reduction, basically, any data set has multiple features, right? So like my height, my age, my ethnicity, my blood pressure, that sort of thing, right? You may be thinking, well, not all of those kind of data points or features of this data are important to solving this problem, but dimension reduction can tell you what is most statistically important and what is not. And so if you can drop specific features using dimension reduction, you can actually solve some of the supervised and reinforcement or deep learning problems a lot faster, because it's one less dimension that you have to understand for your models. So these are just some examples of how you can use different forms of learning. Like for our Forte 1.0 work, we're using supervised learning and unsupervised learning, right? We're developing, we have, at the end of our outputs, we have a set of data, and then we want to cluster them to be able to find out like what segments do different users belong to, right? And clustering does exactly that. You see in this picture here that there's kind of like three different clusters. But in reality, sometimes you don't have very thoroughly defined clusters, different groupings, right? Sometimes they can kind of mix around, there's outliers, right? And dimension reduction can actually help with that, because if you reduce the dimensions, then you're reducing the noise in the data. And if you can drop those out, you could therefore get better clusters and different groupings that are more accurate to the problem that you're trying to solve. So it's all really kind of interesting, but unsupervised machine learning, different from supervised learning, doesn't depend on labeled data, and really you don't really need to know too much about your data set actually to be able to kind of look at things. But it typically helps to have a domain expert in the space to be able to tell you yeah, actually, I don't think ethnicity has something to do with whether or not you'll have, XYZ diagnosis down the road. This is probably all false medical information, so just ignore me, but take this with a grain of salt, and these are examples. All right, we don't have any questions yet. Feel free to ask. This is kind of like the third area of learning, different ways of learning for machine learning models, right? It's this area called reinforcement learning. So in reinforcement learning, you're not necessarily trying to get probabilities, get more insights into functions. You're not trying to solve the problem using a function. You're actually trying to model this problem as a reward versus a punishment kind of scenario. So in reinforcement learning, you can solve more complex problems because it's not limited by a sort of linear function that you develop or that this model kind of learns, because we all know that, if you have a linear function, or just take a very simple linear function, right? You have just this line, there are different various points that exist in this kind of space, and a line may not be the best approximation for that. And so in reinforcement learning, you're kind of navigating the world and modeling the world in the sense that you get rewards or you don't get any rewards for certain actions or predictions that you take. And this is really great for evolving models of learning for use cases like predicting the weather, where it's not as straightforward as saying, well, this Saturday it rained and this Saturday didn't rain, so there's a 50% chance that the next Saturday it'll rain. That doesn't really tell you the answer very well. And, in predicting the weather, there's so many different features, and maybe instead of looking just at Saturdays to be able to predict Saturday's weather, you need to look at Monday and Tuesday and, like so many more dimensions. And so it's really great for that kind of use case. It's also great for multi-agent simulation and game theory. So if you want to be able to simulate what a potential game is like with like 5 or 6 different players, if one player goes this way and another player goes this way, well, what should you do as the output or as that player? So reinforcement learning solves kind of a lot of these problems, right? And the nice thing is that there's a lot of advancements in the space right now that makes a lot of these learnings and inferencing times almost real time. So that just makes it even more viable, and something that's a continually growing field is deep reinforcement learning, where you're using neural networks to inform and basically solve these reinforcement learning problems. And that's a picture of a neural net right there. I don't know. I like to kind of like set this as an example because deep reinforcement learning is kind of taking a lot of the principles that we're learning in deep learning and applying them into reinforcement learning, and then bringing it back into the deep learning community so that we can continue to solve different kinds of problems. But again, like machine learning and deep learning, deep learning is a subset of machine learning, and you want to be able to, you can solve like, you can use neural nets to solve supervised machine learning problems. It doesn't just have to be reinforcement learning problems. But again, like the way that you learn and what the output is well, the output is slightly similar, but the way that you learn is different, right, for all 3 of these models. And so to recap, right, there are 3 different ways that a machine learning model learns, right? You can have the supervised type learnings, where you can build classifiers and regression models that will tell you yes or no, or give you a numerical output if you're solving a regression problem. There's also the unsupervised learning, right, where you can do different things like dimension reduction and clustering to better understand your data sets. And then there's the reinforcement learning aspect to this, where you're trying to model the world as a sort of rewards and punishment kind of game. So I went over a short foundation for machine learning models, what they are, how do they learn, right? What are the different use cases? So what's the actual, what's the actual process, and what do we mean when we say we're training something, and why does that sound slightly different from when you're deploying something? Well, what are all the different steps, right? And what do we even want to focus on for the remainder of this session? So with, oh, sorry, does anyone have any questions? Nope, awesome, cool. So yeah, I've mentioned learners, models, right? But how does it actually become this tangible application that we're building out in the future, right? And I kind of, right here, I have an outline of the kind of steps or phases that we bring a model into, right? From preparing the data to training it, to packaging it, validating it, maybe having to go back, right? In this kind of cycle, just so that we can deploy it and kind of understand like what is the performance of our machine learning models? Like, is this application viable? How are we doing in terms of performance, et cetera, et cetera. But I wanted to kind of focus in these two areas for this session because I think it's really applicable to, it's a really great way to kind of begin to understand what does it take to deploy learners and, you know, different models. So again, like I just want to recap, you get some input, you get some data as input, you know, it could be labeled, be non-labeled, whatever it ends up looking like, right? You use that data to train a learner, and then that learner can output some type of decision or some, you know, make some kind of decision for you. And that's basically what you use to wrap up different data applications, right? So what does that actually, what does it take to actually do all of this? Yes. Okay, so the first step is really about preparing data, right? And like I mentioned, in a lot of supervised machine learning use cases, you have to label that data, and labeling is expensive because, you know, as I mentioned, it doesn't come for free either. You know, if I have a data set full of animals, you know, I have to be able to say, is this a cat? Is this a dog? Yes, no. Maybe I even have to say what animal it is, you know, in order to be able to build a system that can tell me whether something is a cat or a dog or something else. So it's really important to be able to kind of have someone who's thinking about the data set and be able to determine like what are the appropriate labels, and even be able to go back and say, well, we need more a data set that has, you know, more features or that is more informative, you know, and that's not even the beginning of a lot of the issues that we may have. You know, I shared this example of medical data and collecting medical data around, you know, someone's age, someone's blood pressure, someone's insulin levels, right? But in reality, some of that data may be missing. And when it is, you have to kind of figure out, well, what statistically makes sense for us to be able to still solve the problems that we do when we have missing data. So in this example here, I have some Python code that's reading in a diabetes data set. It's a CSV file, but you know, this can pretty much look like anything, right? It can be data that we scrape from the internet. It can be data that we pull in through Google Analytics, but basically we read in that data. And then now you want to filter that data set based off of missing data fields, and then replace some of those missing values with something else. And sometimes, you know, you replace zeros with the mean value. You know, say for example, I'm missing some insulin levels, maybe for data points that are missing that information, I just put in the average value, or instead of putting an average value, maybe I put in 0. But again, that goes back to talking to the domain experts and figuring out, you know, how bad is it if I put a 0 in for insulin levels versus the average, right? And this can basically skew our learners, right? Because if we're feeding in really trash data that's not accurate to the real world, then we're not going to be able to realistically build applications that can predict these things, right? So that's just something to note there. It's just that there's quite a bit in this space that requires some finessing, you know, and then there's also the aspect of being able to have enough data, right? And I always like to bring up this this kind of conversation around having a training, a test, and a validation data set, because it's super important that the data that we train models with is different from the data that we use to evaluate the performance of our applications, right? And also bringing in the aspect of, well, what happens when you want to tune certain parameters of the model, you know, certain different functions, different ways of learning, right? What happens if you want to tune that? You need an additional data set to make sure that you're not overfitting on specific data. And then there's also another aspect around imbalanced data sets, right? Which can make learning a lot more challenging. Say, for example, I'm trying to build a system that can detect diabetes. If I don't have enough data that says negative, that has negative cases, then I may not realistically be able to accurately estimate those things. So these are all really important aspects that we have to think about, right? And so while we may start with a full data set, in reality, once we begin to build out a training set and a testing set, we may not actually have enough data to be able to have the model learn fully. And this is a problem that happens quite often in deep learning, where you have so many different layers, and in order to get, beyond like a 50% accuracy, you just need more data. And no matter how much you tune it or try to change the model, you just don't have enough data to be able to inform certain decisions. And so this is something that can happen quite a bit in the data science world. All right, cool. So I talked a little bit about some of the data preparation type things, some of the issues that may happen when it comes to preparing data, and just beginning to think about the different models that we'll use, like how does that data even have to be set up, right? So now we can kind of discuss more about what does it take to actually train the model, right? I have this training data set, and now I'm making sure that this model, this black box that I have, learns based off of that data and develops some type of function approximation, especially in this is in the case of supervised machine learning, right? I have some type of model that I learned, maybe I have a classifier, right, in this green box. I have some training data. I have this learning process that I'm going to have these two go through, and then at the end of this learning process, I have a model that's approximating some type of function. And so whenever it sees some type of input, I can say with some reasonable amount of confidence that it's XYZ output, yes or no type situation. So, all right, what does it look like in code? Right here, I have sklearn, scikit-learn, which is a popular library that gives you some of these classifiers or some of these different models that you can use to learn, right? And so it's as simple as taking this data set here. I have I have the full data set X and Y, and I want to split it into a test set and a train set. And I also have a classifier. I'm using a decision tree model. So if you're familiar with binary trees, right, you can basically build out a binary tree based off of the data that I'm going to feed it. You can train the model by doing a classifier.fit function. So this fit function is, what we do to get that approximation. And then after we get that approximation, we've taught the learner, right? We can go and get the results using a predict function. So this is typically the very standard flow for how we train models and begin to even do this type of work. You'll commonly see this, again, like you may not be using a decision tree, you may be using a linear classifier, you may be using a deep neural network. There are different libraries that can help provide this functionality. You can even build your own custom one. That's typically what happens in kind of the deep learning space is, we use PyTorch or TensorFlow to build our own models, and boom, you can solve, your problems in a very kind of bleeding edge way. But at the end of the day, you have to feed it in your data, you have to fit it. Sometimes it's called something else, and then predict the results and be able to get those results. And after you get those results, right, that's when you can actually evaluate performance, and that's when your test set actually comes into place, right? So this test set hasn't been used to teach the model anything, but we're using it as sort of a benchmark to be able to evaluate performance, right? So this test set will say, based off of these predictions that you made, are you right? Are you wrong? What's the accuracy? And a lot of times when we're evaluating performance, we can sub out different classifiers. We can sub out different models. So, I can not use a decision tree and just use a classifier. And then I may get a certain accuracy score, and I may get a different accuracy score with a decision tree. But again, like I now can benchmark those performances, right? And so with a linear classifier, very simple kind of classifier that doesn't require a lot of any tuning, right? Any numbers or anything special, I can see what my benchmark or baseline score is versus, building my own custom model. I want to be able to see, like, what score can I accurately kind of approach, right? Say, for example, I have really bad data. And so, my baseline numbers are 60 or 70%. Well, okay, that's a little better than guessing, right? Can I reasonably get 70 or 80% accuracy using a different model that I custom build? So that's kind of how that's how we begin to approach these things. And there are different measures for performance depending on your data set. Again, like I mentioned, you can have a very imbalanced data set, and then you may want to look at something else like, precision versus recall, or balanced accuracy versus just standard accuracy, where you may have more of a balanced data set, and that happens. So it's just important to kind of note, like, how important are false positives, false negatives? Like, is it a trade-off? Do I want one or the other? Because at the end of the day, that's all it is. It's a lot of trade-offs in this game. And most of the time we're trading off, like, the amount of data that we have, the time it takes to train versus performance and all this other stuff. And, it's very similar to the things that we trade off when we're building software engineering applications. So what happens after this? I shared some more information about preparing data. I also shared information about what it's like when you're training. So what actually happens after we have this model that's learned, right? Oftentimes we'll save and export that trained model so that we can, and again, like I said, training, like, it was going to take this short amount of time, but, sometimes it takes months or weeks before it's fully trained. And so what will typically happen is you'll export that model that's trained, and then you'll be able to productionalize it, deploy it, and then use it in inferencing. And in inferencing, it's when you kind of toss in, like, the live data that you're seeing, and then you want that output, right? So there's quite a bit of work that goes on in that space, because when we were training, it was kind of this experiment that we were doing, right? And oftentimes that work is done in a Juniper notebook that's done as scrap, right? It's done haphazardly because we're still kind of like researching and experimenting. And in reality, though, that's not the kind of code that we actually deploy and productionalize. And so there's typically steps to take that involve, like, integrating the code into an actual code base, putting it into, production ready mode, and that sort of thing. And then, also being able to track and monitor those applications once we have them out. So that's kind of the work that we're doing with Forte 1.0 or 2.0 as well. Moses has been working on, training the model, deploying it, going back, trying to see what's going on, even taking some of the work that we have in Juniper notebooks and converting it into actual Python code, like code in a Python file, right, that can be deployed and productionalized. So, commonly things will be found in Juniper notebooks, and it has IPYNB as a file extension. But I hope that gives you a good understanding of sort of the things that happen in this space, and why it is that, it sounds kind of confusing when we talk about testing and training and unsupervised and supervised learning. It's because there's so many different approaches that we can take to solve our problems, and there are even ways to optimize in this space. And so this has been like work that's been studied and researched, and people are, we're now coming to different realizations about what works well, but it'll continue to change as we go on in this space. So that's the 101 on machine learning. I hope that helps you kind of navigate the world. And when we begin to talk about different approaches in the ML and data science space, I hope this, this continues to help you all kind of understand where we're coming from and begin to figure out or find your way through some of the concerns that we may have as it relates to these different data projects. Again, like I'm always open to conversations about this. We're actually opening up more hiring opportunities on our team. So if you know anyone who's interested in this stuff, I have a lot of ideas. We have a lot of amazing projects, an awesome team. So ping me. And if you have any questions about this session, I'm free to answer any and all of them. So feel free to do that. But thank you all.
Hi, Tiffany. I have a question.
Yes.
So in your learnings and working in this type of environment, what's, say, one of the cooler applications of all this technology, aside from Forte, of course?
Yeah, there's some really amazing stuff. And a lot of it is open source too. So it's really incredible to kind of see like this. I'm trying to find my screen. Okay, it's not happening. It's not happening. But it's really cool to see different things happening in the space and being able to try them out yourself. There's one company called OpenAI. I'm not sure if I've talked about it yet with you all in this group, but it's a nonprofit that aims to open source and democratize different AI solutions. And so they have something called GPT-3, which is a natural language processing model that actually understands language at a really high, like at a really in-depth level, where it can build out different solutions. So I've seen people build talks based off of GPT-3 models that are trained. I've also done work where I've fed it like different blog posts that I've written in my writing style, and it'll adopt that and be able to generate hot takes. So it's really cool to be able to see like those kinds of situations. In terms of like actual applications and things too, there's like a lot of really great work that's being done by Facebook AI. They're actually doing a lot of really great work that's quite similar to the work that we're doing on our revenue data projects. So there's a lot of similarities there, and they've been open sourcing different data visualizations for deep learning models. So you can actually see how at each stage, like what kind of part of the model is learning specifically what for a particular problem. So they have visualizations on the object detection stuff that I was showing you. So at each kind of training interval or each layer, you can see what it learned and output that. And so data visualizations is another area that we're hoping to get into as well as a team, because it's so important to be able to begin to understand like what these models are learning, and is it different or is it similar to how the human brain learns specific topics and comes to, their own conclusions.
Cool, thank you.
Yeah. Yeah, I love this stuff because I think it's always interesting to talk about sort of a lot of the developments in the space, especially because like I mentioned in the last revenue show and tell, a lot of the deep learning and reinforcement learning findings didn't happen until like the past 10 years. Reinforcement learning, it was more viable. It came to be more viable in the 90s, but at least for deep learning and deep reinforcement learning, that's all stuff that's post 2010. And so people are still finding ways to make it more viable and like get the results that it needs to get in order to solve some of these problems. It's really, really cool.